I'd like to introduce our next talk, which is by Christoph Gade, and this is from the National Decommissioning Centre, and his talk, Cuttings Piles as Dynamic Geochemical Interfaces, Rethinking the Legacy of Offshore Drilling in the North Sea. Christoph.
Thank you. Okay, well, thank you very much for giving me the opportunity to talk about a passion of mine, which are cuttings piles. To frame sort of the title that is probably ballooned a bit out of proportion, the focus of today's talk will probably be just more about the term dynamic, which is something that is, at least in my opinion, not been considered when it comes to cuttings piles up until now. So, about 2 years ago, I presented at this very conference, I presented some research that we had done at two former BP sites, Miller and Northwest Hutton, and we had taken samples from those cuttings piles. So what this basically looks like is that here on the left is Miller and here on the right is Northwest Hutton. During drilling operations for the wells of these platforms, significant amounts of the cuttings material, so the seabed that was displaced, was discharged and formed these mounds. Now, we don't know exact data for all platforms, but we have a pretty good inventory for what was discharged at Northwest Hutton, which was, in engineering terms, lost to the environment. Now, they reckon that it was about 52,000 tons of cuttings, 26 million litres of hydrocarbons. This would be mostly classified as kerosene-like or diesel-like. This formed a cuttings pile of about 31,000 cubic meters. To put that into perspective, that's a mound that is about 5.5 meters high and covers an area of about 200 by 150 meters. So the reason why we can literally see it in the bathymetry is because it is a physical thing on the seabed. Now, back then, I analyzed samples that we had taken for mercury. And the results were, to no one's surprise, the closer you get to where the platforms used to be, so the closer you go to the top of that cuttings pile, the higher the concentration of mercury would be that you find in it. So this is, the dashed lines indicate where the platform used to be, and from there on it's a pile. But what I thought was striking is that, at least for Miller, it was pretty obvious is that the concentrations that we found in sort of the top 5 centimeters of the core samples that we took was consistently higher than in the second part, so 5 to 10 centimeters of depth, and then still higher than the ones at 10 to 15 centimeters of depth. So this was very obvious here, but the same pattern emerged at this site as well. And I thought, well, you know, for one, it might have been a fluke, but what if it wasn't a fluke? So back then, we asked the question, is there an underlying reason for this type of pattern that we see? Well, I suggested that, well, there might be a mechanism to it, or some motion in the ocean. So cuttings piles, when they form, are quite this sort of unique geochemical environment because, on the one hand, you have huge amounts of oxidizable hydrocarbons. Again, remember, 26 million liters of diesel. You have a high ionic strength because, of course, it's discharged into the seawater and then compresses on top of each other. And what we know from previous studies is that, similar to in sediments, at some point you reach a point of anoxia the deeper you go. But in sediments, this might take a meter or 1.5 or even 2 meters. For cuttings piles, complete anoxia is reached within a few millimeters of you going into the pile. So this is quite an interesting reactor that you formed there. Complete anoxia and a high concentration of all kinds of contaminants. Heavy metals, mercury is the least of our worries when it comes to this. And so, okay, well, what could happen? Well, one of the things that happens in normal sediment geochemistry is that you have reductive dissolution of sort of your ferric and manganese oxyhydroxides. Those are both elements that are easily dissolved under these conditions, so minerals that dissolve in these conditions. But what that also means is that by dissolving them, you suddenly inject a whole lot of sort of free electrons into your reactor. Suddenly that stuff becomes active. So you kick off a load of redox potential that previously wasn't there. Okay, so what does that then entail? Well, again, in normal sediment chemistry, you have sort of a redox mobilization of previously stable minerals. So stuff that, if you were to buy it at your nearest chemistry shop, it would say it is insoluble in water. Well, under these conditions, suddenly it does become soluble. And again, nothing new, something that we've known about sediment geochemistry for a long time. But what was then interesting, and what separates a cuttings pal from your normal sediment, is the type of minerals and the types of elements that are suddenly being mobilized. So for your sediment, you'd be interested in iron and manganese and maybe even a smidge of cadmium. But here you're talking about large concentrations of lead, mercury, of also cadmium, but sort of all the things that, you know, the public doesn't really like to talk about because, you know, they sound scary. And then the reason was, okay, cool, so, but why is the concentration at the top higher? Well, if at the top surface you have an oxidative climate, again, in your pile you have anoxia, well, stuff gets taken, from a chemistry perspective, stuff gets taken out of solution. So if someone at the top consistently takes away something, and if you still want to maintain an equilibrium in your system, well, then stuff has to move upwards, following the laws of diffusion. So you would get this sort of creation of a diffusive gradient. But this was all just a pipe dream, because again, I just had data for mercury for just the top 15 centimeters. So what was there to do? Well, there is further evidence. So more than 20 years ago, there was some kind of good reporting done by the UKOA in 2001, and they looked at cuttings pals at depth, and they found that, okay, for certain elements, for example, for mercury and for barium, what you would get is this surface accumulation. So in the case of mercury, our idea was, well, there are certain redox and ligand-driven mobilization processes that drive this. For barium, we know from normal sediments that it sort of tracks what are called organoclastic processes, so processes where organic matter is broken down. The diesel that is down in these cuttings pals gets broken down at the surface. So this makes perfect sense. But apart from surface accumulation processes that we found, or that are reported here, there are also the exact opposite. We have deep pore water enrichment for some of these elements, and especially for stuff like arsenic and lead, where the concentration increases with depth, because it gets mobilized, but instead of traveling upwards, it travels further into the pile. It's quite nice for lead. I also have a picture of a literal piece of lead mineral from an SEM session that I did with some of those Miller and Northwest Hutton sediments. So, okay, well, they did this for almost 2 meters depth for cores, but, you know, can any of this be replicated? Well, I don't have the means, I must admit, to go out and sample cuttings pals just on, you know, a normal Tuesday. But what I am able to do, absolutely, is to do some modeling work, you know, and it is way easier because, again, this reactor that I'm describing to you hasn't run since yesterday or since 3 or 4 or 5 or 10 years. It's been running so for 40 years, for 50 years, depending on the age of the cuttings pal. How am I to replicate in a lab something that's been going on for decades? Well, again, you can do diagenetic modeling, and this, again, exactly what I've done. So I've set up a one-dimensional column diffusion model. So, you know, we have a core, basically, everything that I've shown you before. I approximated, because that is incredibly difficult, the mineral composition within the cuttings pal. There are probably way more minerals in there, but at the moment, I do not have the wherewithal to identify every single one of them. There's an equilibrium-driven thermodynamic control of the whole thing, and I let this model run for, you know, just 40 years. Why not? Seems to be a good average point to start. Well, what are the outcomes? Well, it mirrors exactly what the report and what my own findings found. For certain elements, in this case, just as an example, for mercury and barium, the higher you go, the more to the surface you go, the more these are enriched. Whereas for other, again, for lead and arsenic, the deeper you go into the pile, the more they enrich there, and it slowly gets depleted over time at the surface. So this is quite amazing, because what are the implications of this? Well, first of all, sample material taken close to the surface may not reflect the total pile load and grossly misrepresent the degree of pollution. Currently, OPRED, as far as I know, and I'm happy to be disproven, OPRED operates on the idea that if you as an operator in your EIA give them a number, this is the amount or concentration that we found at the cuttings pile, that they say, okay, cool, that applies to the whole pile. That is wrong, because you might either way overestimate the amounts, see mercury, see barium, or you might severely underestimate, see lead and arsenic. But it also means, and I'm probably sort of doing a bit of kerfuffle here, but the current practices that are in line with guidance like OSPAR 2017 of reporting total concentrations are, in my opinion, regressive and do not provide a basis to adequately risk assess whatever we find in offshore cuttings piles. I'd like to thank, for the initial study, of course, the University of Aberdeen Marine Directorate, who were kind enough to take me out offshore, the National Decommissioning Centre, of course, and please forgive me, but I have not mentioned Chevron, who were the original funders of the BP Miller and Northwest Hutton study. Thank you very much.